Welcome to the Crazy Hat Chemist. So I hope you're having a great day. Good morning, good afternoon, and good evening. And this is where all your chemistry needs are met. So today we are going to be going over the covalent bonding worksheet number 1. And hopefully this is going to be an awesome worksheet here for you as well, like many of the others. So before we get started on this, we're going to go over a few items. Number 1, you're going to make sure that you have a periodic table. And you're going to know the valence electrons. So, valence electrons. How many valence electrons are there in each element? And so what we're going to be covering is covalent bonding. And with that covalent bonding, there's one valence electron in column 1. That's 1. There's 2, 3, 4, 5, 6, 7, and excluding helium, 8. So those are the number of valence electrons that we're going to be dealing with, and these go within these columns. So for example, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium all have 1 valence electron, just like boron, aluminum, gallium all have 3, just like oxygen, sulfur, selenium all have 6. Argon and krypton and xenon have 8. And beryllium, magnesium, calcium, strontium, they have 2. Carbon has 4, silicon has 4, nitrogen has 5, and phosphorus has 5. Fluorine, chlorine, bromine, and iodine have 7. So those are the number of valence electrons. It's critical that you know that information before we move on to the worksheet. In addition to that, other critical information that you need to know before we actually get moving on to this worksheet, and that's the following. So this is the covalent bonding handout that I have made. And so you're going to go to the video, The Crazy Hat Chemist on YouTube, and go to Honors Chemistry 6, the bonding collection, bonding 28 molecular geometry. So if you go to this video here, it describes exactly what this entire chart means, and you really need to be familiar with this chart. You do need to know certain things about this, okay? So let's go over some of those poignant items here right now. So central domains, 2, 3, 4, 5, and 6. We're not going to do anything more than that. There are bonding domains and non-bonding domains. Bonding domains are where we have pairs of electrons, and non-bonding domains are lone pairs of electrons on the central atom. I'm going to follow what I call the axe. The A is the central element. So I'm going to scroll right up here just a little bit so you can see this here. And this VSEPR theory, the valence shell electron pair repulsion of VSEPR theory, which uses the concept that from a central atom, electron domains will be separated as far away in a 3D space as possible. This allows one to identify and determine the shapes of molecules or ions based on this simple concept that electron domains repulse one another and therefore move away from each other. This theory is simplified by using the letters A, X, and E to represent the word X, which represents a generic formula of a molecule or an ion. The letter A represents the central atom of a molecule or ion, or at least the portion of a larger molecule being assessed. The letter X represents the atom or atoms attached to the central atom. Excuse me on that. The attachments X to the central atom may be the same or different types of atoms. The letter E represents non-bonding or lone pairs of electrons attached to the central atom. Okay, E can never be lone pairs of electrons on the outside atom or atoms as X. Okay, so that's what the X represents. The A is the central element. So you see in this column here of A, of the X, there's only one A. There's only one A ever. X are the atoms attached to the A. So there could be 2, there could be 3, 4, 5, there could be 6 atoms attached to the A, the central element. And then the E's are representing lone pairs of electrons attached to the A. And with this AXE geometry, this axe geometry, you can get a molecular geometry or a molecular shape. And so, for example, AX2 is linear, and that has a bond angle of 90. Is it polar? Well, that's why that asterisk is there. And it says if the molecule or ion is asymmetric, then the molecule or ion is polar. If the molecule or ion is symmetrical, then the molecule or ion is nonpolar. Okay. So there's a column for molecular geometry that coincides with the axe. So every time you have AX4, it's tetrahedral. Notice that I've bold-faced some of these: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These are the basic 5 structures: 1, 2, 3, 4, and 5 structures. Those basic 5 structures do not have any lone pairs on the central atom, and they can be represented by these central domains over here. The number of domains on a linear is 2. Number of domains on trigonal planar is 3. Number of domains on tetrahedral is 4. Number of domains on trigonal bipyramidal is 5. And number of domains on octahedral is 6. There are bond angles, and this is associated with the central element and the outside elements. And then there's molecular polarity. Some molecules or ions are polar just based on their shape, effectively. So in order for something to be polar, it must have polar covalent bonds, and it must be asymmetric. And then we have hybridization, which is kind of like a correction factor for the valence bond theory. And that valence bond theory has some incorrect components to it. And so hybridization fixes that. That's hybridizing orbitals, just like you have a hybrid car or something like that. All right, so just give me a moment here, and we're going to go over some of these basic shapes, and that will help you get a better understanding of what's going on here. All right, so hopefully this will give you a better understanding of these shapes. So you really need to make sure that you build models of all of these, and that will give you the following. So I highly recommend that you get yourself a molecular model kit. From that molecular model kit, if we have something that's AX2, that would be linear. And here's an example of something that is AX2. This is the A, that's the central atom, and these are the X's, these green things right here, okay? And this gray part is representing a bonding pair of electrons. So we have our central A and 2 X's, that is linear. The bond angle for this is 180. And since the 2 X's are the same, then that means that this shape is, that means since the 2 X's are the same, that means that this is nonpolar. If you were to change one of these X's from one element to another element, then it would be asymmetric and polar. It's sp hybridized, and how you determine that is from the central atom. You go sp1, and that's sp hybridized. Okay, let's try the next shape. Okay, the next shape is trigonal planar. Trigonal planar looks just like this right here. And so trigonal planar is AX3. And so it's it's the central atom, X1, X2, X3. And so it's X1, X2, X3. That's trigonal. See, it's trigonal, 1, 2, 3. That's trigonal, and then they are planar. So all the atoms are within the same plane. If you take a circle, which is 360 degrees, and you divide that 360 degrees by the number of bonds that you have, which is 1, 2, 3, or the number of outside atoms, that's the X's, then you get 120 degrees. So this is 120 degrees here. So each of this bond angle right here is 120, this bond angle is 120, and this bond angle is 120. This is sp1, p2 hybridized. Again, these gray sections here represent the bonding electrons between the central A and the outside X. Right now, what we're going to do is we're going to take this basic shape, but we're going to remove a bonding pair of electrons, and then we're going to get a non-bonding pair of electrons. And so this larger tannish one on the central atom is an E. So it's a lone pair of electrons on the central element. Now you should see that the basic shape there is the same, except this one is A, X1, X2, E, and that is still sp1, p2 hybridized. This shape is angular or bent. It has a bond angle that is most certainly less than 120. So lone pairs of electrons compress bond angles, right? Compressed. Smash them. So lone pairs of electrons on the central atom compress bond angles. And this is asymmetric. So this is not the same, in other words, and that makes this polar, right? So that is a 3-domain structure, right? Central domains, a 3-domain, okay? So we're going to pull these off to the side. We'll refer back to them. Now we're going to go for the tetrahedral, trigonal, pyramidal, and angular or bent structures, okay? And so this is going to be the tetrahedral-like structure right here. A for the black one, E A for the black one, X for the white things here. So it's A, X1, 2, 3, and 4. The bond angle here, this bond angle, this bond angle, and this bond angle are all the same at 109.5. So these white things are at the corners of a tetrahedron. So if you've ever played Dungeons and Dragons or something like that, then you have multi-side dice other than the 6-sided dice, and maybe that will give you a reference as far as their shapes. Okay, so this is a tetrahedral. Now, if you take this basic structure right here and you remove a bonding pair, then you replace it with a lone pair of electrons, then you get the following. This is the lone pair of electrons. This is the E. So the blue thing here is A. Then we got 1, 2, 3 X's and 1 E. So this is AX3E, which means that this is trigonal, 1, 2, 3, trigonal, pyramidal. It's a pyramid, right? So it's most certainly different than the trigonal, trigonal planar that we had before. Okay, and it's hard to see that blue one right there. I noticed. So hopefully you see the difference between these. And you should see that the blue central atom here on this trigonal pyramidal structure is not flat. It's not on the same plane as the white ones are. Okay, so that's what that looks like right there. So we'll put that off to the side. And then just notice that these are all kind of aligned in the same orientation. We're going to do another one in the same orientation, and it's right here. Okay, and you should see that these are very similar. Okay, certainly very similar. They all have 4 domains around the central atom. Okay, but this last one here is A for the red thing in the middle, X1, X2, and E1, E2. So this is AX2, E2, and this is bent or angular. And this is the classic example of a compression of bond angles with lone pairs of electrons on the central domain. So on the left-hand side with the central atom as the black one, that has bond angles of 109.5. With this lone pair and this central atom being blue, then you have a compression of bond angles of 107. Then you add another lone pair of electrons on the central atom right here, and you have further compression of bond angles at 105. Now, these are not set bond angles in stone. They can vary, and so each molecule is certainly different than the next one. But in general, that's why we have tetrahedral 109.5, trigonal pyramidal 107, and angular or bent 105. Now, this is the second angular or bent. I hope you notice. Now, These two structures, that is trigonal pyramidal and angular or bent, of these two structures, they are asymmetric just based on their molecular geometry. They are not similar, therefore they are polar. Both of these are polar, so anytime you get trigonal pyramidal or angular or bent, it will most certainly be polar. All right, let's move on to the next domain, which is a 5-domain structure here. In the 5-domain structure, you have the most number of shapes here that you can have possibly have. That's trigonal bipyramidal, that's AX5. Then there's disphenoidal seesaw, AX4E. Then there's T-shape, that's AX3E2, and then linear, and that's AX2E3. Okay, so this right here is trigonal bipyramidal. It's trigonal, that's within the plane, there's trigonal. And then bipyramidal, so there's a pyramid on the top and then there's a pyramid on the bottom if you look at that. So you should see that the trigonal structure is rotating, and then you have the poles that I'm holding on to with my fingers right now. Okay, so if you were to put a lone pair of electrons, oh, by the way, so making sure this is just like the trigonal planar structure within the plane here of this. So it's the same, and that's why that plane has 120 degrees. So there's 120 degrees, 120 degrees, 120 degrees, 120 degrees. Whereas at the poles between the central is going to be 90, and that's hopefully plainly obvious, 90, 90, and 90. So if you were to place a lone pair of electrons on this, that is remove, then you need to think about where is the most space. So we have a possibility of either 90, sorry about that bell there. We have either a possibility of 90 or we have 120. And so what is larger? 120 is larger. So that means that the lone pair is going to go within the plane at the 120 region. And so that's why this lone pair cannot be at the poles. And so this structure is disphenoidal or seesaw. And so hopefully you see the seesaw shape there. I'll turn that here. You see the seesaw shape. This one is asymmetrical, most certainly, because this lone pair makes this an asymmetrical shaped structure, and therefore it's polar. Now, there is a compression of all these bond angles, and typically these are compressed and these are compressed away from this lone pair. Again, if we were to take another lone pair of electrons, so this is, by the way, this disphenoidal seesaw is AX4E, AX4E. This is the E that I'm holding on to. There's the A, that's the central atom in purple. Now, if we were to take another lone pair of electrons and add this to the central atom, what do we get? The next shape, and that's T-shaped. So you should see that on the T-shaped, we're going to bring the disphenoidal out, but on the T-shape, you have the lone pairs again on the central region. They cannot be opposite each other because then it's a trigonal planar structure. But this T-shape is generally viewed as something that's 180 and 90 here. Okay, it is most certainly asymmetric, absolutely asymmetric. There could be a compression of bond angles on this as well, and that could happen as well. Now, if you take another lone pair and add that, where does it go? In the central region again, and that is the next structure right here. So I'll pull away the T-shape. And this is now the second linear that we're coming across. I hope you understand that the AX2 was a linear structure, but it had no lone pairs on the central region. One of the common mistakes that students make is that if it has lone pairs, it's polar. This is an example of something that can be non-polar because it has lone pairs that cancel each other out in the central region, and this is most certainly linear. So this structure right here, which is linear, this is the T-shaped, the disphenoidal, and then the, let me see if I can fit most of these in the same screen here. And then trigonal bipyramidal in shape. Whoa, let's see if we get that trigonal bipyramidal in shape right there. All right, so hopefully you see that all of these have the same hybridization. And that is, we'll just pick one of these, and it doesn't matter which one we pick, but they all have the same hybridization. So that's S, P1, P2, P3, D. S, P1, P2, P3, D. S, P1, P2, P3, D. And then you can clearly see that with this trigonal bipyramidal structure. That is S, P1, P2, P3, D. They all have sp3d hybridization. All right, so it's critical that you understand the hybridization on these. And if all the green ones are the same, then this is non-polar. But as I mentioned before, there are some of these that are polar. All right, so let's pull these away, and we're going to go into our 6-domain structure, of which there are not nearly as many again, but we'll do that one. All right. All right, so this is our, this is our 6-domain structure, and this is octahedral. So it is going to be AX6, okay? So A for the central atom, X1, X2, X3, 4, 5, and 6, okay? This is right here. You should see that this has bond angles of 90. No matter how you turn it, it has bond angles of 90. So this is octahedral. Okay, and many people are confused, like, wait a second, you're just showing me a structure that has 6 things on the outside. Where is the octa coming from? And the octahedral is coming from this shape that it has 8 sides to it. So if you were to look on this head on, then this is like a, instead of a trigonal bipyramidal structure, it actually is a tetrahedral, it's like 2 pyramids on top of each other, right? So just like the pyramids of Giza or something like that. Okay, so what we have is 1, 2, 3, 4 faces, and that's one of the pyramids, and then there's 1, 2, 3, 4 more faces underneath. So it's like a pyramid on top of a pyramid. That's why it has octahedral in shape, and it has 8 sides. Okay. So again, if you play Dungeons and Dragons, or if you're familiar with multi-sided die, then that would hopefully be helpful. All right, so if we have an octahedral structure and we want to put a lone pair of electrons on that, then it doesn't matter where we do that because all these bond angles are 90. So now we have the next one right here. So we're going to pull away the octahedral structure, and this is AX5E, and this is a square pyramidal. So hopefully you can see the square right there, and it's a pyramid. Okay, so square pyramidal structure here. So a square pyramidal structure is going to be asymmetric because this is by definition, since it's asymmetric, it will be polar. So that will make sense, hopefully. And these have a compression of bond angle. So the bond angle is less than 90, and that will hopefully make sense as well. All right. And then we have the next structure. If we take away a lone pair of, if we take away a bonding pair of electrons. Now, remember, the lone pairs have to be as far away as possible. So that means that we are going to have this structure right here, and this is AX4E2. And for this one here, this is a square planar. You should see that all the green things are within the same plane, so it's square planar. And again, this is another example of having lone pairs of electrons that is nonpolar, provided that all the green atoms are the same. All of these octahedral structures are sp3d hybridized, and I'll just go over this one here, sp1, p2, p3, d1, d2, so sp3d hybridized, all right? Fantastic. All right, so now I'm going to pull this away here, and we're going to go on to the next little kind of concept here. And the next concept is polarity. And so I'm going to use 2 bar magnets to maybe have a better understanding of polarity. So when something is polar, that means that it is asymmetric. Okay, so for example, this is asymmetric, and it is most certainly polar. Whereas this right here is symmetrical and it's non-polar. This is asymmetric and it is polar. And this is symmetrical and therefore non-polar. So a bar magnet is polar. It's asymmetric. There's a north and a south side. Or if you want to, you could say that there's a positive end and a negative end to it. And so there's a positive end and a negative end. And as you can clearly see, with this polarity, the magnets will align themselves up. That is the same case with molecules. If you have more than one molecule, this is a representation of two molecules, one molecule, two, second molecule. When they are polar, they will align themselves up just like the magnets do, because they will align themselves up by attaching to each other with their poles, their magnetic poles. Really key concept here in this unit. So I'm going to pull away these magnets here for a moment, and then we're going to go on to the next topic here. So in order for us to really fully understand all of this Lewis dot structures, we are going to come up with the rules. And here are the rules of which I have. Okay, so let's see if I can fit this all on one little bit here. Here we go. So these rules are critical for your understanding, and I would highly recommend that you watch the Crazy Hat Chemist video, Honors Chemistry 6, the Bonding Collection, Bonding 11, Lewis dot structure rules. And that video sets up all the rules here, but I'm going to briefly go over the rules here just right now. It says sequential steps for drawing Lewis dot structures. You're going to sum the total number of valence electrons. There is no ownership to electrons. Follow the rules below for placement. A. Add for each negative charge of an ion on an ion and subtract for each positive charge on an ion, as noted above. Number 2, determine the central atom. This is the least electronegative element. However, it cannot be hydrogen because hydrogen cannot branch. The central element is designated as A when determining the geometric shape name using the Vesper theory. Number 3, place the additional atoms in a plus sign pattern surrounding the central atom. These are designated as X when determining the geometric shape name using the Vesper theory. Number 4, place a pair of electrons between the central atom A and all the surrounding outside atoms X. This is a single bond, or known as a sigma bond. Number 5, if electron pairs remain, place a pair of electrons on the surrounding outside atoms X as lone pairs of electrons or non-bonding electrons. Number 6, if electron pairs remain, place the remaining pairs of electrons on the central A as lone pairs or non-bonding pairs of electrons. These lone pairs of electrons on the central atom are designated as E. Number 7, verify the octet rule. The vast majority of atoms and elements follow this, and the duet rule, and that applies to hydrogen only. Check for the exception to the octet rule. Boron and beryllium can be electron deficient, that is less than an octet, and this is acceptable. Period 3 or greater, periods 3, 4, 5, 6, and period 7 can exceed the octet rule, that is, these elements can have greater than an octet. Carbon, nitrogen, oxygen, and fluorine must obey the octet rule in all circumstances. Lithium and neon do not apply. In fact, these elements are not typical in Lewis structures. Number 8, to satisfy the octet rule, multiple bonds, double or triple, may be necessary by sharing electron pairs. Double bonds are formed with a combination of a sigma and a pi bond, and a triple bond is formed with a combination of a sigma and two pi bonds. Common mistakes that students make are, number 1, making a double bond with a hydrogen atom. Hydrogen only has 2 electrons and always follows the duet rule. That is 2 electrons. Number 2, placing lone pairs on hydrogen atoms. Hydrogen atoms again follow the duet rule and can never have more than 2 electrons and a single bond, a sigma bond. Number 3, double bonding a halogen atom. Fluorine, chlorine, bromine, or iodine, when the halogen is not the central atom, a very unusual event in and of itself. Halogens are very electronegative, and in order to make a double bond, electrons must be shared, and consequently, halogens, being electronegative, do not share electrons. And then I'm going to add in 2 more things here at the end. There are resonance structures. If there are double bonds of which can be placed in different positions, resonance structures are possible. This occurs when there is more than one valid Lewis dot structure, and some molecules have multiple resonance structures with the movement of these double bonds. Keep in mind that not one of the resonance structures correctly represents the bonding electrons in the molecule, but a fusion of all the resonance structures would. However, any resonance structures will provide the proper molecular geometry, hybridization, polarity, and bond angles. One thing that I don't have on here on this one, and you would have to look at my advanced placement chemistry videos, and that is the separation between various different resonance structures. And that is done with another component. And that is another calculation, which I will discuss in another video. And then we have geometric isomer structures. Geometric isomers occur when there are alternate Lewis structures where the physical arrangement of the atoms differs. Any isomer will give the correct molecular geometry, hybridization, and bond angle. However, the polarity can differ with different structural isomers. Typically, cis and trans structures exist with geometric isomers. And I'm going to be covering resonance structures and geometrical isomers within this worksheet. So hopefully that will work well for you. Again, I am the Crazy Hat Chemist, the Crazy Hat Chemist. Please watch my videos on YouTube. And if you are learning something right now, then please subscribe and give me a thumbs up. And again, I answer all my comments, so make sure that you throw in a comment every now and then. Here we go. Now we're going to get moving on our worksheet finally. All right, so hopefully that gave you a firm understanding of this material. So we're going to be referring, or I am going to be referring back to this worksheet constantly, and I'm going to be referring back to this worksheet constantly right here, these two handouts. If you do want this handout, then you can shoot me an email, and I might be able to send you this send you this in an email as an attachment or something like that. So you can shoot me an email. So here we go. We're going to start off on this worksheet here. And here is our first worksheet. So again, I'm going to be referring back to this concept here and these rules. I'm going to be following these rules in order. I'm also going to be following the periodic table and the number of valence electrons that is critical to the understanding of this entire video here. All right, so here we go. Let's get moving on this here. So let me zoom in just a little bit more so that we have as large of space as possible on this. Okay, perfect. So here we go. All right. So Xe has 8 valence electrons. There's one of those. Oxygen has 6 valence electrons. There's one of those. Fluorine has 7 valence electrons. There's 4 of those. I'm going to add all those up. That is a total of 42. And this is what I like to do. What I like to do is take the total number of valence electrons and then divide by 2. That will give me 21 pairs. And I find it easier to actually work with pairs than with anything else. Pairs enable you to do the problem much faster. So here we go. The least electronegative element is going to go in the middle. So that's what we're looking for, is the least electronegative. So let me go over one more item with you here. And we need to find out what is the most electronegative element. So the most electronegative element is fluorine. The most electronegative element is fluorine. So very rarely, if ever, will fluorine go in the middle. The least electronegative element is francium. Okay, so we're finding out what element is furthest away from fluorine. And then the rule is, but never hydrogen. You can never have hydrogen as your central element because hydrogen cannot branch. So we're looking for the atom that is furthest away from fluorine. Okay, that's what our goal here is at this moment. That least electronegative element is going to go in the middle, and that's what we're looking for our central atom. Okay, let's see if we can. Perfect. So the least electronegative element is going to be the xenon here. And it's certainly farther away than fluorine. and there's lots of fluorines, and it's certainly farther away than oxygen. In fact, the noble gases hardly have an electronegativity at all. Okay, and then what we're going to do is we're going to place the other elements around the xenon, kind of like this, the face of a clock, actually. So the next element is oxygen, and doesn't matter. And then you have a fluorine, a fluorine, a fluorine, and a fluorine. So what I've attempted to do is to draw this such that the xenon is in the middle, and then the elements surrounding it are completely surrounding it, approximately equal distant. Okay, now I'm going to place these 21 pairs of electrons. The first rule is to place a bonding pair of electrons between the central and the outside, central and the outside, central and the outside, central and the outside, central and the outside. So I've used up 1, 2, 3, 4, 5 of my 21 pairs. The next rule is to place lone pairs of electrons along the outside elements. And you cannot do that with hydrogen. So lone pairs on the outside elements. So that would be, so I've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the reason I stopped at each one of these, and now I have 20 pairs of electrons, is that what I'm going to do is draw in pencil here. And what I'm going to do here is draw in pencil, and this is what you're going to imagine in your mind. Okay, the reason I stopped at has 3 lone pairs of electrons around each of the oxygen and each of the fluorines is that in your mind, you're going to circle each element here. And that light circle that I'm drawing here in pencil is not something that you actually physically write down. You just think about it. And I'm going to count up 2, 4, 6, 8, or 1, 2, 3, 4 pairs, 8 total electrons. That's an octet. So I really don't write that down, so I'm going to erase that. Okay, and then I'm going to circle this one as well here. And I'm going to think 2, 4, 6, 8. That's 1, 2, 3, 4 pairs. That's 8 total electrons. That's also an octet. And so that's where I'm ending. That's why I'm not adding more lone pairs of electrons to all these atoms here. I have used up 20 pairs, and look, I have 21. The next rule is to place lone pairs of electrons on the central atom there like that. Try to color coordinate that as much as possible. Okay, now I'm going to ask another question, and that is the xenon, the central atom in the middle. Okay, does it have an octet? Well, it has 2, 4, 6, 8, 10, 12 electrons. That's certainly greater than an octet. Can it have greater than an octet? Well, xenon is period 3 or greater. So that's period 3, period 4, period 5, period 6, period 7 on the periodic table. And anything that is period 3 or greater can exceed the octet rule. And just confirming where the periods are on the periodic table, and that is period 1, 2, 3, 4, 5, 6, and 7. So it's period 3 and greater can exceed the octet rule. And it looks like here that xenon right here is most certainly greater than period 3. It's actually in period 5. So can it exceed the octet rule? Absolutely, most certainly. All right, so now what we're going to do is we're going to get the molecular geometry or shape name. And how I get this is making an X. So the A is the central xenon. The X are the atoms attached to it. So that's 1, 2, 3, 4, 5 of them. And the E is the lone pair of electrons on the central atom. And that's an E. So what does that correspond to? That is square pyramidal. Okay, so that AX5E is square pyramidal. And so what I highly recommend that you do is you actually have this entire section here memorized. You're going to spend time memorizing this so that you will actually know what these are. So you can draw the axe, have the name of the shape associated with it, the bond angle, and you can calculate the hybridization simply. Okay, hybridization is the next column, and we're going to get that. And the hybridization is really simple. We're going to count up the number of domains around the central atom, but we're going to count them up. So it's going to be S, P1, P2, P3, D1, D2. So this is SP3, D2 hybridized. Again, this is a correction factor on the valence bond theory. And you can find out more about the valence bond theory if you were to watch my videos, the lecture series. All right, the next one is getting the bond angle. So this is an octahedral structure here, but since it's square pyramidal, it will have a bond angle that is less than 90 degrees. This is an asymmetric molecule, so this is polar. And there are no resonance and there are no isomers. So making sure that you understand the square pyramidal structure, and this is the square pyramidal structure right here. It's a square. You can see the square. I'm holding on to the square portion, and it's a pyramid because this kind of pops up above the plane. And it's pyramidal with this lone pair. This lone pair also makes it asymmetric. What I'm holding on to is the lone pair, which is represented by the red lone pair of electrons on the central atom. Okay, and you should see that this is asymmetric. That means that it's polar. It has polar bonds and it's asymmetric, therefore it's polar. Right? That one is our first one, and hopefully that check done. Perfect. All right, let's give the next one a try. Okay, the next one is right here, CH2Cl2. So using, again, our periodic table and getting the number of valence electrons, 4, and there's 1 of those. Valence electrons, 1, and there's 2 of these. Valence electrons, 7, and there are 2 of those. So that's 4 times 1 plus 1 times 2 plus 7 times 2, and I am going to get 20 electrons. And like I said before, I am going to be dividing by 2 so that I get pairs. I will have 10 pairs. So now I will have 10 pairs of electrons. So I'm going to look on my periodic table and find the least electronegative element, the one that is furthest from fluorine, but not the hydrogen. So since it's not the hydrogen, it can't be the hydrogen. So I either have a choice of either the carbon or the chlorine. And the carbon is most certainly least electronegative. So that means that the carbon is going to go in the middle. I'm going to draw 2 different structures here because I have seen 2 different structures from my students, and I'm going to show you both of these structures, and hopefully that will help you out in distinguishing between the two and not distinguishing between the two and understanding that they are actually truly the same. So following the faces of a clock, that is 3 o'clock, and then we have 6 o'clock, and then we have 9 o'clock, and we have high noon. I'm going to place the 10 pairs of electrons as is appropriate. So that is bonding pairs of electrons first. That's 1, 2, 3, and 4. And then lone pairs. I cannot place lone pairs on the hydrogen because it has following the duet rule, of which is right here. So I'll just circle this right here again. I'm doing this in pencil. That is a duet rule. Hydrogen cannot have any more electrons around that. That's why you are not putting lone pairs on the hydrogen like this. That's incorrect. There is no circumstance of which that will be correct. So therefore, the lone pairs, I've used it 1, 2, 3, 4, and then lone pairs 5, 6, 7, 8, 9, and 10. And then you should clearly see that this chlorine has an octet. This carbon has an octet. This chlorine has an octet. This hydrogen has a duet. This hydrogen has a duet. I do all that circling in my mind. I don't actually physically do those circles. So hopefully that makes sense for you. So I'm going to erase all that stuff right there because that's not really correct. All right. Okay. Fantastic. Now what we're going to do is get the X from this. The A is the central element, that's the carbon. The X are the elements that are attached to the central element. There's 1, 2, 3, and 4. Are there any lone pairs on the central atom? No. There are lone pairs on the outside atoms, but those do not count as an E like what I've drawn here. Okay, and I'm just going to designate this here. I'm going to draw this in red there that you can clearly see that that's the E, and the X's are the other elements attached to it. So AX4 is tetrahedral. I'm going to get the hybridization, and that's sp1, p2, p3, sp3 hybridized. Tetrahedral corresponds to a bond angle of 109.5 degrees. And then we need to figure out whether this is going to be polar or non-polar. And I'm going to draw one more Lewis structure so that you can see the two potential Lewis dot structures here. So again, central atom is carbon. And then I'm going to have a hydrogen. And this time I'm going to put a chlorine here, and then a hydrogen here, and a chlorine here. This is the other common way that I've seen this written. And you can actually rotate this 90 degrees as well as rotate this 90 degrees. It doesn't matter. Bonding pairs of electrons between the central and outside, that's 4, then 5, then 6, then 7, then 8, then 9, then 10 pairs of electrons. It's following the same thing that we have over here. This is AX1, 2, 3, 4. That's tetrahedral. It's sp3, sp1, p2, p3 hybridized. That has bond angles of 109.5. Now I need to figure out whether it's polar or non-polar. And so I'm going to get the structure here for you, and then that will help you out. Okay, so some people think that this one is polar, and some people think that this one is non-polar because it looks like they cancel each other out. But you have to truly understand this tetrahedral shape, okay? And the basic tetrahedral shape that I showed you before was right here. Now, this tetrahedral shape is showing that all the bonded atoms are the same element, and that is not the case here. So what we need to do is make another model, and that other model is the following right here. The whites are representing the hydrogen, and the greens are representing the chlorine. The black in the middle is representing the carbon, okay? And you should see that the chlorines are not actually opposite each other, right? They are not 90 degrees from each other. The chlorines are actually not 90 degrees next to each other either. See, all these bond angles here are 109.5. So that yields to this structure here like this. And so really, if it's polar, then it has polar bonds, and you can draw what's called a molecular dipole. And a molecular dipole is an arrow like this, if you will. So can you draw a molecular dipole? Most certainly you can. This molecular dipole means that these things here are a very electronegative, so that's why it has the pointy end of the pole, and that is facing away from the other atoms. Okay, and so because you can draw a molecular dipole, this is polar. That means it's asymmetric. Another way to draw this is the following. What is the difference in electronegativity between carbon and hydrogen? Well, carbon is more electronegative than hydrogen. So then I'm going to draw a bond dipole. Carbon is more electronegative than hydrogen, a bond dipole. Then chlorine is more electronegative than carbon, a bond dipole. Chlorine is more electronegative than carbon, a bond dipole. This is a molecular dipole. A molecular dipole is the sum of all the bond dipoles. And if you can draw a molecular dipole, that molecule is polar because it is asymmetric. That is, if you look at this molecule has a side here that is different than this side. That is asymmetric. Okay, just like a bar magnet that I aforementioned over here. And this is a good representation of this here, where I have a positive end of the bar magnet, that's right here, and the negative end of the bar magnet, that's right here. Remember the pointy end of the arrow? When that hits you, that is rather sharp and that hurts, ouch. So that's why that's the negative end. All right. Is there any resonance or isomeric structures? That is a no on this. So we're not going to do that one. All right. All right, now we're going to do the next one here and see how this one pops up. So the next one is SEI 6. And so we're going to look at our periodic table. Selenium has 6 valence electrons. There's 1 of those. Iodine has 7 valence electrons. There's 6 of those. So it's 6 times 1 plus 7 times 6. And that will yield us 48 total electrons. Remember, we always divide by 2. I'm going to get 24 pairs. Okay. All right, fantastic. We're going to have the least electronegative go in the middle, but never hydrogen. And most commonly, the halogens never go in the middle unless we are forcing them to. So we're going to have that selenium in the middle. Notice that there are 6 iodines, so they are going to be equidistant away from the selenium there. So 1, 2, 3, 4, 5, and 6. All right, so we have our 24 pairs of electrons. Our first rule is to place, notice I didn't mention this on the other 2 Lewis structures. Whoops, let me give this here. There we go. I did not mention this on the other 2 Lewis structures, but this is one of the most other common mistakes that I see students doing. And that is when they draw the atoms, the elements, that is, when they draw the elements, they immediately draw the bonds. That is incorrect. Do not do that. It is one of the most common errors that students make. And I have done it correctly on the 2 previous ones. I draw the atoms, but I have not drawn the bond between them first or while I'm drawing the atoms. No, don't do that, because then you have a tendency to miscount. Okay, now I have 24 pairs. I have no bonds, no lone pairs, nothing. Now I'm going to place these bonding pairs of electrons between the central and outside, 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 central and outside. Okay, that has used up 6 pairs of electrons. I'm going to use up 24. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have used up my 24 pairs of electrons. I'm going to circle this iodine that has 2, 4, 6, 8. This iodine has 2, 4, 6, 8. So the iodines have an octet. That's 8. That selenium has 1, 2, 3, 4, 5, 6 pairs. Is that okay? Well, is selenium in period 3 or greater? And the answer is yes. Selenium is in period 4, so that's not a problem whatsoever. Okay. All right. Fantastic. Now we got that handled. Now what we need to do is do the X. So the central element is an A, that's selenium. Then I have X, that's 1, 2, 3, 4, 5, 6. Are there any lone pairs on the central element? That's a no. Okay, so therefore AX6, this is octahedral. Hybridization, S, P1, P2, P3, D1, D2, SP3, D2. Bond angles, if it's octahedral, are 90 degrees. So octahedral is this structure right here, and we had talked about that last time. So there's octahedral, okay? This has bond angles like what they look like, and that is 90, okay? These are all the same element all the way around, so therefore it is symmetrical, and this is non-polar. And there are no resonance or isomeric structures for this one here whatsoever. So we're good to go with that one. All right, so let's see how many more we have. We have quite a few more problems here. Okay. But what I'm going to do is I'm going to do a couple more and let's see how we can carry on through there. How about that? All right, so moving on to the next sheet of paper here. So pulling this one away, moving on to the next sheet of paper, we're going to be following the same pattern that we did on the others. Okay. All right. So this next one here is a carbonate. So that's a polyatomic ion of which you should be familiar with from the nomenclature unit. Okay. I'm gonna have this up here so that you can clearly see that as well. There we go. Cool. All right. So carbonate, 4 and 1 and 6 and 3, and then right here. This is a polyatomic ion. It has a charge of -2. Now, when we are doing this, we are totaling up the number of valence electrons. So we are going to add 2 for this. If it was a minus, it was a 3 minus, then I would add 3. Okay. If it's positive, then I subtract. Okay. All right. Hopefully that works for you. So now what we're going to do is we are going to count these up. We have 4 times 1 plus 6 times 3 plus 2, and that will give me 24 electrons. Remember, I always work in pairs. That is the fastest way to do it. And so I will have 12 pairs. The least electronegative goes in the middle. And so that would be the carbon. And then I'm going to place the other atoms around it. So we're going to have one here, one here. And we're going to place our 12 pair. Again, notice another thing that I have not done is I have not drawn the bonding bonds yet at all. Haven't done that. Don't do that. Okay. So 12 pair between the central and outside. 1, 2, 3. Then outside. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So now what we need to do is we need to check for the octet rule. Octet rule satisfied. Octet rule satisfied. Octet rule satisfied. So every oxygen has an octet. So I'm good to go with that. Now, the carbon in the middle is lacking an octet, and carbon is one of 4 elements that I aforementioned. That is carbon, nitrogen, oxygen, and fluorine, which must absolutely have an octet. So I need to make it such that this carbon has an octet. And I've used up my 12 pair. I can't add in another pair. I can't have 13 pairs. That's impossible. So what I'm going to do is I'm going to move a pair of electrons from one of the oxygens. And the question is, which oxygen? And then the answer is, it doesn't matter. So I'm going to move a pair of electrons. Sharing is caring. So I'm going to put, so just notice that this oxygen and this carbon, okay, this oxygen has 8. When I remove these 2 electrons and I place it in here for a double bond, this oxygen still has 2, 4, 6, 8. Now the carbon has 2, 4, 6, 8. So now the carbon now has an octet. Okay. So the question is, why did I use this lone pair on this oxygen? And the answer is, I don't know. I just chose that one. Could I have used this one into here? Yes. Could I have used this one into here? Yes. But I can't do all 3 of them. I can only do one of them at a time. So what I'm going to do is I'm going to get a new fresh sheet of paper and then do all of these. Okay, so what is going to happen is we are going to have what are called resonance. We're going to have resonant structures, okay? But what we can do is answer all the questions based on this structure right here. So I'm going to get rid of the circles, and here we go. So our molecular geometry is A for the carbon, X for the oxygens. How many oxygens? 3 of them. So this corresponds to trigonal or trigonal planar. Remember, trigonal or trigonal planar looks like that right there. It kind of looks like, man, that's an airplane. Okay, here we go. Bond angles of 120 degrees. Hybridization, sp1, p2. So sp2 hybridized, okay? And the molecular polarity. So all these are the same. So therefore it's symmetrical and non-polar. Okay. So now what we're going to do is we're going to do one more thing here, and we're going to really truly draw all the necessary resonance structures for this here. So really, this is going to be crossed out, okay? But I'm going to rewrite this one and add something more to it, okay? So I'm going to peel this off to the side for just a moment, leave this a blank white sheet of paper here, and then we're going to do it right here for all the resonance structures. So these are the resonance structures for carbonate. So I'm going to redraw the one structure of which I drew before, okay? And that is looking like this. Notice that there are no lone pairs on the central atom. Okay, that's what makes this trigonal planar and not trigonal pyramidal. Okay, so this is the correct Lewis dot structure for carbonate. Now we do need to draw resonance structures. So resonance structures, what we're going to do is do a double-headed arrow in between them. We're going to draw the atoms in the same orientation that we had before. There are actually a total of 3 resonance structures for this. So we are drawing the atoms in the same orientation. Okay, and I chose to begin with on the very first structure to share a pair of electrons from this oxygen and bring it in here. Well, why not this one? So that is, I'm going to make this one a double bond. And notice that if this one's a double bond, then it will only have 2 lone pairs of electrons, and the other ones being single bonds with 3 sets of lone pairs of electrons. And then we have one other option, and that is the top oxygen could be a double bond and then 2 lone pairs, because that gives an octet, single bonds for the other oxygen carbon bonds, and 3 sets of lone pairs of electrons. That also gives an octet. Okay, so some critical things here is one other. Because this has a charge to it, we're going to put this in brackets and the charge up here, just like it normally is. So it's carbonate, and that is CO3 2 minus. So I certainly have that 2 minus charge right here and up there in the same location, and that's how you do that. Again, I have these double-headed arrows in between these. I could have used any one of these 3 resonance structures to acquire the shape, the polarity, the bond angle, any of it. It's all the same. Okay, all right. That gives you an awesome foundation to do some Lewis dot structures. So we have some more Lewis dot structures to do. Our next one is going to be BeCl3, but we're going to save that for part 2 of this video series here. So this will be part 2 of this video series, and this is just part 1. So I'm going to end right there and make sure that you are following everything I'm saying, and you're going to do a great job. I'm going to see you next time. Good morning, good afternoon, and good evening.